Hello everyone, I welcome you all for this video session on DC to DC boost converter. So let us see the configuration of the boost converter compared to the buck converter. So here it is the buck converter which we already discussed in the previous videos. So the configuration of the buck converter is the switch is connected in series, the diode is connected parallel, and inductor is connected series, and the capacitor is connected across the load. So then with this configuration we will get the output voltage is less than input voltage. So that we'll call this is the buck operation or step down operation. Whereas coming to the boost converter, or it is also called as a step up converter. The other name for buck converter is step down, and the other name for boost converter is a step up converter, because the output voltage is greater than input voltage in this configuration. So let us see how the configuration will be compared with a step down converter. So in the first change is the inductance which are connected in the second part of the circuit, which will be connected in series to the source, and the switch is connected earlier series in the step down converter. It will be connected to parallel in the boost converter. Now the diode is connected series again in the circuit, so this configuration will become a boost converter configuration. Now let us see the operating principle of this boost converter. The key principle of that drives that boost converter is tendency of the inductor to resist the change in current. So because the inductor is connected in series to the circuit. So there are two modes of operations in the circuit. The first mode of operation is when the switch is on condition, and the second mode of operation is when the switch is off condition. Now, so mode 1 is the on state when the switch is closed, when the switch is on. So here the switch is connected, that switch, when the switch is closed. When the switch is closed, the current flows through the source, inductor, and this short circuited path, inductor in the clockwise direction. And inductor starts storing the energy from the source, and the polarity is from left to right, and automatically the diode will be reverse biased, and the load is connected. This circuit will be disconnected, and the load current will be circulated in between the load and capacitor. Now in the mode 2 operation, when the switch is open, then obviously the current will be reduced as a impedance is higher. So therefore the change in reduction in current will be opposed by the inductor. Now the inductor earlier stage it stored the energy, now it will act as a source and it start giving the energy. So now there are two sources connected to the across the capacitor. So one is the input voltage and another one is the inductor. It's also stored energy. That energy is also start giving. Now thus the polarity will be reversed, because it's earlier it is a charge, now it starts giving energy. So as a resultant, there are two sources will be in series. So the one is the input source and inductor source. This will charge. So higher voltage to the capacitor. The capacitor voltage will be higher charge. So that high voltage compared to source voltage, it will be added your inductor voltage, which will be both will be charged with the capacitor. That voltage is applied across the load. So that's why the boosting operation will take place. So here the switch is open and only path offered to the inductor current through the flyback diode D, the capacitor C, and the load. Now using the KVL and KCL in the average sense, the average values are normally the average value of the voltage in the inductor is 0. The average value of the capacitor current is 0. So when the switch is closed condition, the first mode of operation, when the switch is closed, considering the time period dt, when the switch is closed for the time period dt, so diode is reverse biased, automatically only this circuit will be closed. So that the current DIL by dt, the inductor current DIL by dt is equals to, so the equation is equals to V in by L for a dt seconds, the time assuming that the switch is closed for the time dt seconds. So if the switch stays closed, then input will be short circuited in the steady state condition. Now, second mode is when the switch is open for 1 minus dt seconds. So second mode, mode 2, so the switch is open, then your voltage, input voltage and inductor voltage will be applied across the capacitor. So assume the inductor voltage is equals to, one side of the inductor is Vn and other side of the inductor is Vout. So the inductor voltage Vn minus Vout. Then the inductor current in the second mode of operation is equals to dIL by dt is equals to Vin minus Vout by L value. So this diode will be closed inherently, assumes in conduction mode. So since the average voltage across the L in steady state condition is 0, so then we'll write the equation during the on condition d time. So d into Vn, the voltage across the inductor is Vn, and a time period of switching on mode 1 operation is d. And second mode switch is off condition 1 minus d Vin Vout. So these two are coming from these two conditions. So first condition is Vin voltage, second condition Vin minus Vout. So first condition time period is Vin into d, second condition is Vin minus Vout into 1 minus d. So we can write a d into Vn plus 1 minus d into Vn minus Vout is equals to 0. Then we'll get a simplified equation. Vout into 1 minus d is equals to Vn, d Vn and dn and gets cancelled. So finally the output voltage, input output voltage relation will get V output is equals to Vin by 1 minus d. So a realistic gain value, what is the gain value, is approximately normal boost converter. So we'll use it from 4 to 5 times. That means the output voltage will be greater than input voltage approximately 4 to 5 times. So that is really upper limit of gain value for the boost converter. Maximum will operate at 4 to 5 times. So this is the equation waveforms of boost converter in the continuous current mode of operation. So this is the output voltage. This is the switch on condition. When the switch is on condition, the input voltage is Vi. So when the switch is off condition, the output voltage is Vi minus Vout. So the current will be rises when the switch is on, and the current will be drops when the switch is off. Again the current will be rises, current will be drops. So when this dropping condition, this point is not equals to 0, so that the current is not never becomes 0 at any part. So it will be a continuous current mode of operation. So while examining the inductor current ripple, so the maximum value of inductor and minimum value of the inductor, so depends on that the current nature will be decided, whether the current is a continuous current or discontinuous current. So when the ripple value, whatever the minimum value, IL minimum value reaches to 0, and it will, if it stays for some time 0, or at least it touches the 0 point, then we are calling that is a discontinuous mode of operation. If this minimum value of the current is not reaching to the 0 point, then we are calling that is a continuous mode of operation. So here in this diagram it is shown the current value of the minimum inductor current is not touching the point of 0, so it is a continuous current mode of operation. So here it is a two parts of variation of inductor current. One is when the switch is closed, the inductor current will be raised. So we are assuming inductor current is equals to dIL by dt. So Vn by L. And when the switch is open, then your dIL by dt value, inductor current dIL by dt is equals to a little bit larger time, it is a Vin minus Vout by L. So it depends upon your L value. So normally the value, whether it is touching to 0 or not, it depends upon the L value. So the average value of this, the inductor current is in between half of the value we are taking the average value. So if you are taking a complete ripple is the delta I, so then the average value is, so your value of the middle of this point. So you assume the continuous current in L, or you assume the peak value is 2I in, then we can calculate 2IN is equals to, here the tip is 2IN, we are assuming that 2 times of input current, then Vout minus Vin divided with L boundary condition into 1 minus dt, half period is switch open condition 1 minus dt. So here Vout we can represent it as Vin by 1 minus d from the input output relation, Vin L boundary 1 minus d into t. So that the L boundary condition, that means at where just it touches the 0 point is called your boundary condition. Otherwise, from continuous to discontinuous, the point occurs, that point we are calling just it touches the 0. So that point is L boundary. The minimum value of inductance value. So V in D by 2I in F. So this 2IN is nothing but delta I, change in I value from minimum to maximum. So then we are considering the worst value of D, it's a 1. Then your L value for getting a continuous operation, if you want to get a continuous operation of your boost converter, you have to maintain your L value this quantity. So your L should be greater than V in delta I F, right? So if you are maintain this L value, then you will get a continuous mode of operation. If your L value is equal to this value, then you will get a boundary condition, exactly this point touches the 0. So if this value is lower than this value, then it will have some time period of 0 current, and then again it rises the current. So that is the boundary continuous mode of operation, depends upon L value. If it is a L is a greater continuous mode of operation, L is equal to this value, it is a boundary condition between the continuous and discontinuous, and L is lesser than this, then we will get a discontinuous mode of operation. So use these values and minimum and maximum values. Now let's see the discontinuous mode of operation. If the ripple amplitude of the current is too high, that means the delta I value is too high, the inductor maybe is completely discharged before the end of the one cycle, commutation cycle. So normally this will happen in the conditions of light load condition. Here the current through the inductor falls to 0 during some part of the period. So as the inductor current at the beginning of the cycle is 0, then maximum value IL max is equals to VI dt by L. So it's the on period of IL max. So during the off period, during the off period, on period IL max, and off period VI minus V out delta T by L. So that delta period, off period, we can call VI D V naught minus I. So here it is the waveform of discontinuous mode of condition. Here you can observe. So during on period, inductor current will be increased, and during off period it will be reached to 0, and it will be sustained 0 some part of the period. It is a delta and a delta 1. So this mode of operation we are calling a discontinuous mode of operation. Now, so we'll see the impedance matching between impedance matching between the source to load to transfer the maximum power from input to output. So it's a simple maximum power transfer theorem. If you are calculating your R value, such a value that if the impedance matching is happened, then the maximum power will be transferred from source to load. So this is the equivalent circuit where we can calculate the R value equivalent source prospectus. Then you will calculate the R equivalent value, which value is equals to V in by N. So Vn is 1 minus D V out divided with I out 1 minus D. So that will calculate 1 minus D square R load. So naturally, when this boost converter is connected to solar panel, depends upon your output resistance of the DC to DC boost converter, your maximum power transfer condition will be considered. So here it is a characteristic, VI characteristics of your solar panel, it is the output voltage and short circuit current. So if you are considering a maximum power panel, when it is a 6.44, so you will get a 130 watt, it is the ideal condition of getting a maximum power. But if you are if you use this resistance, load resistance, then you will get a maximum power. But when you change your load resistance, 100 watts, suppose 100 ohm resistor, if you are connected as a load resistance to your DC to DC boost converter, the maximum output power you will get 14 watt ohm. So this is observe the variation. When you connect a load resistance approximately this one 6.44 resistor, then your value of maximum power you will get a 130 watt. But you connect a 100 ohm resistor directly, extract only 14 wattage of the power. So this is the variation of it will influence the load resistance because of the impedance matching conditions. So R equivalent value 0.7. Now we'll see the condition of boost converter design. So worst case component ratings, how you will design it. Suppose we are assuming input current is 10 amperes, output voltage is 120 volts, output current is 5 amperes. So V out is 120 volts diode side. V out is 120 volts. We already considered. Input current is 10 amperes. Now we'll consider your input inductor current. If your input current is 10 amperes, your input inductor current is approximately 9 amperes. So because 2 by root 3 times of I. Output capacitor voltage, whatever the connected, it should be 1.5 times of your V out voltage. So if you will maintain, if it is a output voltage 120 volts, then we will maintain 250 volts capacitor. Then output capacitor current is a 5 amperes, approximately it is a 5.66 amperes. Then diode and MOSFET voltages, it should be 2 times of your output voltage, so it's nearly 250 will maintain. So diode and MOSFET currents, which are approximately 16 amperes and 20 amperes. So second condition will calculate, that is a boost voltage peak to peak. Voltage value, peak to peak value, you can substitute that value, it's a 0.67067. We observe it is a very low value. You can vary your capacitance value. Once you vary your capacitance value, this voltage peak value will be varied. So here it's consider 1500 microfarad, then your voltage ripple is this one. So if you vary your C value and switching frequency, then obviously your value of the voltage ripple peak to peak value will be varied. And another condition is the minimum inductance value needed to guarantee continuous conduction. Just if the L value is greater than this, then we'll get a continuous conduction mode. Otherwise, so we'll get a discontinuous mode. If your value of this one you can calculate, so 42 IN is 222 and frequency 50 kilohertz, then you will calculate, you will get a 200 microhenry. So all over, so we'll get the conditions of L value 100 microhenries, because if you maintain less than this, you will get a discontinuous. If you get a continuous, if you want to maintain continuous, you have to maintain. So it is a L value 100 microhenries, 9 amperes, C value 1500 microfarad, 250 volts, 5.66 amperes, and diode is 200 volts, 16 amperes. So MOSFET we have to select 250 volts, 20 amperes. So this is a simple design steps of your boost converter. Thank you very much for giving patience on this lecture. So we'll meet you again in the next lecture. Thank you.